let's now take a look at the idea of emphasis regarding proportions. Specifically, we want to calculate a confidence interval for pi, the true proportion, to population proportion. Now, it's important to always understand that confidence intervals are always about population parameters. We use them to estimate a population parameter. We do not use them to estimate sample statistics. Estimating a sample statistic really does not make a lot of sense. You know what the sample statistic is. You just calculated it. It comes from your sample data. So why estimate it? You have it. It's a parameter value that you don't have. It's the parameter value that you want. It's the parameter value that you're trying to estimate using the sample statistic. Now, previously we've talked about the idea of the central limit theorem applying to sample proportions. And what we said was that under the right conditions, we know that the sample proportion will be attributed normal, and the mean is pi. Remember, this value is going to be the mean of the sample proportions. And the variance, that's sigma squared for the sample proportions. The variance is pi times 1 minus pi over n. Now, what are those right conditions? The first one we said is that if n is at least 20, which is really not that big of a deal, but the next two really are a big deal. N times pi is going to be at least 5, and n times 1 minus pi also should be at least 5. Now, I'm saying that this is not a real big deal. If n's not quite 20, who really cares as long as these other two are satisfied? Well, I'm not going to go into justification why that's so, but I do want to point it to that is my opinion, and that's the way I teach my students. You should probably check with your professor because they feel that the n at least 20 is an important criteria, and they want to make sure that you address it. So make sure you check with the professor and see what they think about that. Under these conditions, we can say that this assumption that p hat's normal is a reasonable thing to assume. Now, we can use this knowledge to help build a confidence interval for pi. Now, the general form of the confidence interval will be the point estimate, and the point estimate will be p hat, the sample proportion, plus or minus, we use ME to represent the margin of error. So I'm going to have the point estimate in the middle, take this margin of error, add and subtract it, and that's going to give me my endpoints over here to say that I am 95% certain or some level of confidence certain that the true parameter is somewhere in that interval. That's what that's all about. Now, the margin of error for proportions is really determined by a combination of two things. The first one is the level of significance. The level of significance is attached to the idea of how certain we are. And two, the sample size. So these two things actually will determine the size of the margin of error. Now, the sample size, I should probably say a little bit more than that. The sample size is connected to the idea of the standard deviation. Okay. Now, here's what's going on. The confidence interval should look like something like this. P hat, there's a center of our interval, plus, plus or minus the margin of error. And here's my margin of error. Now, first of all, let's dissect the margin of error here. What is the square root of pi times 1 minus pi over n? Well, you know this as being sigma of p hat. That's the standard deviation for the sample proportions, if the central limit theorem applies, if n is big enough. So what is z of alpha over 2? Well, you know what z is. Z is a value from the standard normal. So z, as a value from the standard normal, actually represents the number of standard deviations an observation is away from the mean. It's a z-score. If I take a non-standard normal, convert it to a standard normal using a z-score is the number of standard deviations we are away from the mean. So what's the margin of error? It's a specific number of standard deviations away from the point estimate. So if I use my point estimate as an estimate for the middle, if z happens to be 2, that's saying I'm going 2, here's my standard deviation. I'm going 2 standard deviations away. Well, if I go 2 standard deviations away, 1 standard deviation, 2 standard deviations each direction, based on the empirical rule, we know that about 95% of all my data is in there. Well, what I'm actually doing is I'm constructing an approximate 95% confidence interval if I go 2 standard deviations away. So this value of z will actually tell us how many standard deviations away we need to go. But we've augmented this z with alpha over 2. What does that mean? Well, if I'm 95% certain, if I'm going to do a 95% confidence interval, we think about this as a 1 minus alpha times 100% confidence interval. So if I'm doing a 95% confidence interval, what I'm saying here, this implies that alpha must be 0.05. So if I'm 95% certain that my parameter is in there, I'm 5%, or whatever alpha happens to be, acknowledging that 5% or alpha percent probability that is not in there, that I missed. If alpha was 0.02, 1 minus 0.02 is 0.98, I'd be saying I'm 98% certain that I have the true parameter value. So alpha is my level of significance. And it determines, 1 minus alpha determines my level of confidence. The 95% is my level of confidence. Okay, so still, what's this alpha over 2? Well, if alpha is 0.05, then alpha divided by 2 would be 0.05 divided by 2, which is 0.025. What this is saying is this value right here, this is z of alpha over 2. It's a z value that gives me alpha over 2 in the right tail. Well, because of symmetry, the negative of that z value would, of course, give me alpha over 2 in the left tail. So if this is 0.025 in the right tail, it's also 0.025 in the left tail. Combined, its alpha is 5%. What's that leave me in the middle? Well, 1 minus 5% is the 95%. So this would be a 95% confidence interval. Well, it would be the z value that we need for 95% confidence interval. Okay, using p hat plus or minus z of alpha over 2 times the square root of pi, 1 minus pi over n, it creates a serious problem. Take a look at that for a second. Can you see what the problem is? And the big hint is, why do we construct confidence intervals? What do we use them to estimate? Well, we use them to estimate population parameters. What parameter are we trying to estimate here? Yeah, we want to estimate pi, because we don't know what pi is. But look what's right smack in the middle of the calculation. That's pi. That's what we're trying to estimate. Well, if you have pi so you can do the calculation, why are you trying to estimate it? See, it doesn't make any sense. It's kind of the chicken or the egg argument. Well, because of that, what we're going to do is we're going to change our confidence interval. Say, we don't know pi. So, absent pi, we will use our best estimate for pi, which is p hat. Well, if we change it so that p hat is our best estimate for pi, and this is what my confidence interval is going to look like, then the assumptions must also change. Well, actually, the assumptions are the same. We still say p hat is distributed normal. That's the assumption. But how do we show it's reasonable? Well, we can't take n times pi because we don't know pi. We show it's reasonable if n is at least 20, n times p hat is at least 5, and n times 1 minus p hat is at least 5. Let me fix that hat there a little bit. There we go. So all I did is, because I substituted p hat into my equation here, I'm going to substitute p hat into my satisfying, or the way I satisfy the assumptions. Now notice that this is really the number of successes. Think about it. P hat equals x if x is a binomial random variable divided by n, where x will represent the number of successes. If I'm looking for the proportion of females in a class, I would take the number of females, where observing a female is a success, divided by n. Right? So if I take n times p hat, well, let's just real quick. P hat equals x divided by n, where x is my random variable, like a binomial random variable, number of successes. If I multiply n times p hat, then I'm going to multiply the right side by p hat. That's going to cancel out, and n times p hat is just x. That'd be the number of females, number of males, whatever it is that you're actually looking for. Okay. Actually, this slide just redoes what I just did again. I'll do it again here real quickly. This is saying p hat is distributed normal. That's the assumption. And we're saying it's mathematically satisfied if n is at least 20. N times p hat is at least 5. And n times 1 minus p hat is also at least 5. So if we can show that satisfied, then we can have our distribution, and which is normal distribution. Now we have a way of calculating probabilities, and we can go ahead and do the confidence interval. Okay, so in the next segment, let's take a look at actually applying this proportions and then actually doing a confidence interval.